Poets. Philip's bio is impressive. He's Associate Chair of the Department of Physics and Director of Undergraduate Studies Experimental Nuclear Physics. This is from his profile on the Notre Dame website. His research work involves the development of detection techniques using accelerator mass spectrometry, which has traditionally been used to detect environmental tracers at and below their natural abundance levels. Its main attribute is its power to accelerate and analyze ions of radioactive nuclei with extremely high sensitivity. Well, I don't understand what I just read, but that's why the doctor is here tonight. Philip has been published dozens of times in peer-reviewed journals and has appeared as a panelist on the NPR program Science Friday with Ira Flatow. Is your priceless painting a fake? Better ask a scientist. That was the theme which was discussed, and how techniques from physics and chemistry can help scientists and art historians discover art forgeries. Tonight, Philip will share with us how nuclear physics can help us look under the surface of works of art. And if you'd like to pose a question at any time, please use the live stream chat. As is our custom at the community library, I'd like to make a recommendation from our collection. Tonight, I suggest Pultrachi, The Art of Forgery, through the movie streaming service Canopy, which is available for free with your library card. And of course, a library card is always available free here at the community library. This 2014 documentary focuses on the life and work of Wolfgang Pultrachi, a master forger whose work fooled the international art world for 40 years. It won Best Documentary at the German Film Awards. My runner-up recommendation, however, is How to Steal a Million with Audrey Hepburn and Peter O'Toole. They schemed to steal a forged piece of art from a museum in Paris. It's great fun. However, it's not available through the library. Anyway, now I would like to welcome Dr. Philip Cologne to the community library.
There. Okay. First of all, Carter, thank you very much for this very kind invitation. Thank you, Martha, for having me. Thank you for all of you for having me here. It is always such a great fun to come to Ketchum and Sun Valley. And I have to admit that after a year of having been at home in Chicago, it is nice to be a little bit in the fresh air. So thank you very much for having me here. I'm going to try and not bore you all to death during cocktail hour, because I don't think that anybody will forgive me that. But I'm going to try and explain and talk about something that we do. So as was mentioned, actually, most of my work is in the field of nuclear astrophysics. It is trying to actually understand the nuclear reactions that power stars and basically direct the life and death of stars, and ultimately how we all ended up here. But I promise you I won't bore you with that. Physics has this tendency of getting this sort of look of reaction on people's faces. As one of my colleagues, who's actually an astronomer, always he says when he's in a plane and he does not want to talk to a person next to him, he simply says he's a physicist. And he says that guarantees total silence for the rest of the flight. If he likes to talk, and then he says he's an astronomer. So that's a little bit the case. So how do we come to talk about art? Well, most of our work, as I said, is nuclear astrophysics. Oh, by the way, it will be clearer if I do this. So my apologies. But a little bit of work is what we do is called applied physics, applied nuclear physics. And what I'll try and show is that we do things that are far from the lab. And so let me bring up this slide, which basically is, what is the value of a work of art? Art is art. Art is definitely in the eye of the beholder. That's very clear. But why do we talk about the value of a work of art? I'll get to that in a second. But another question that is very important is, how does an archaeological find, a work of art, fit into the larger picture? Where does it come from? But to the first question, that's the one that we'll be dealing mostly today, art and crime. To quote actually from a 2016 article in the Stetson Journal for Advocacy in the Law, it is widely reported that art theft is the third largest criminal enterprise in the world behind arms and drug trafficking. That's pretty impressive. In 2014, an expert from the Switzerland's Fine Art Expert Institute estimated that as much as 50% of the artwork on the market is either fake or misattributed. Now, why is that important? Because a lot of artwork represent monumental sums of money. Are they fake? Are they true? Does it change the intrinsic work of art? Not necessarily, but its value, yes, and that is important. And that's what we're going to look at a little bit. But not only about fraud, we're also going to look at other pieces of information that we can get. Let's go to this. Basically, the goal and purpose of archaeometry. Archaeometry really is the scientific analysis of works of art or archaeological works. And to quote Aitken, within an archaeological artifact, there is a record to which an archaeologist is blind, but which a physicist can hope to read. Now, don't get me wrong. Physics or science does not answer everything. We bring a piece of the puzzle. Everybody, when you're looking at a work of art, has got to bring a piece of the puzzle. The art historian, the scientist, everybody, and that'll tell you about the real story of this work of art that you're looking at, and ultimately also its value. Not doing that is what most of the story in the next 15 minutes is going to be about, and by the way, goes back to the Pultrachi movie that was mentioned by Carter, because we'll be talking about him. So let's look at a specific case. What this talk will concentrate on is two specific techniques: PIXI, proton-induced X-ray emissions, promise you I won't bore you too much, and accelerator mass spectrometry, which is my field. They are just a small portion of the hundreds and hundreds and thousands of tools that can be used. But let's first look at some facts. So, in the fall of 2011, Germany faced the trial for one of its largest ever case of art forgeries. Up to 53 paintings, mostly by 20th century martyrs, Heinrich Campendonck, Max Pechstein, Fernand Léger, Max Ernst. Those were the artists, most of the works of art. They assumed that the scam started in the 90s, but could have started earlier. And all the paintings were supposedly coming from the Jäger's collection. I'll talk about that in a few minutes. And ultimately, you're looking at millions of dollars that have been lost in this scam. And many art collectors and art auction houses were fooled, and easily fooled. If we look at a work of art here, this is called Red Painting with Horses. It is actually bought by the actor Steve Martin in good faith. He actually happened to sell it for $700,000 just before the whole scam exploded. So he was very lucky in this case. Others were a little bit less. If we're looking here at this, I stole this from Sotheby's. You can see this is a Max Ernst Tremblement de Terre. It was estimated to go for between $600,000 and $800,000 and was sold for $1.14 million. It's a fake. Many were fooled. Who did it? Well, here we come back to Wolfgang Pultrachi, who's now a little over 60, his wife Helen, her sister, and a friend, Otto Schulte-Kellinghaus. Who painted it? Actually, a brilliant artist, Wolfgang Pultrachi himself. He is an absolutely brilliant painter and can paint in the style of pretty well any of these 20th century artists, and did so very successfully. How did they fool everyone? Well, because in the art world, and up to this day very often, the most important part is the provenance. Where does this picture come from? And if you can establish that, and perhaps have a few specialists or art historians that certify it, that is very often good enough. She claimed that all of these paintings came from her grandfather, Werner Jaeger. He did exist. He was a Belgian industrialist. He never had any interest in art whatsoever. And that he had bought all these paintings from a very renowned gallery owner, Alfred Flechtheim. I will talk about him in Düsseldorf. Some of the other paintings also came through the sort of friend Otto Kellinghaus. Who is Flechtheim? Because that is kind of important. So the important thing is, and the first thing to realize is that all of this worked because they stayed away from the absolute, what I'll call mega artists when you're talking about value. They stayed away from the Picassos, the Matisses, and things like that. They went for the second-tier artists, i.e. The German Impressionists. I would very happily have a few of those. but so in that case, that was already very good to not sort of overshoot. So who is Alfred Flechtheim? Alfred Flechtheim was a very famous gallerist in Germany, and he was Jewish. So after the end of the First World War, he had his very large collection, but that he had to give up. Basically, he fled Germany in 1933, moved to Paris, and then died in London in 1937. The only thing that was left from his large collection was a catalogue that described the numerous paintings. Some of them were found back after the end of the Second World War, but many completely disappeared. So what did Pultrachi do? He went through the catalogue, read what the description of the painting was, and painted in the style of that artist. And that was it. In certain cases, they would also have some experts. One of the experts is Max Ernstberg, Werner Spies, who, by the way, was totally innocent in this, except for the fact that he claimed he was a friend of Max Ernst's wife, therefore knew his work and knew that these works of art had been made and authenticated them. And when questioned, he would say, I know what I'm doing, and he authenticated them. To the fact that, and I'll quote this here, the huge shadow of the Pultrachi affair shouldn't detract from Spies's achievements, said Klaus Albrecht Schröder, who was the Albertina director in Vienna. On occasion of this birthday, I would want to honor Spies as one of the most influential art historians of the 20th century. He was totally unknowingly introduced in this, but it really cost him a lot of his knowledge. If we look at some of the works of art, and again, they may not mean much, but all of these works of art are all in the sort of $1 million to $2 million range. They're famous paintings, and these are just the ones that people have found. It is a lot of people think that probably there are at least another 50 paintings that people have never reported because they would be too afraid of the loss of the value. How did all of this sort of appear? Well, the interesting thing is it started with this, the famous red picture with horses. This picture was actually auctioned off by the Berlin auction house Lempertz, and they sold it for 2.9 million to a Maltese company called Trusteco. Sorry, wrong button. Trusteco from Malta. They insisted on an authentication. They weren't too sure, so they actually had an art historian, Andrea Firmenich. She started looking. She basically had written her thesis on the painter of this, and so she started to doubt. She then contacted a Flechtheim expert, Ralph Yench, about two things: one, the sticker on the back of the painting, and secondly, this Jaeger's collection that she had never heard about. And he confirmed that neither the sticker had ever existed on a Flechtheim collection, nor the Jaeger's collection was ever something that he was knowledgeable about. So she actually suggested scientific testing, and that's what we'll be talking about now. As this sort of appeared, people started to look a little bit nearer at works of art that came from this so-called Flechtheim collection. Let me give you a nice example here. These are 4 different paintings, painted between 1905 and 1914 by 4 different painters, André Derain, Max Pechstein, and Fernand Léger. They were all framed in frames in wood from the same tree. That's when people started to look. But up to then, nobody had looked, everybody had trusted where this came from and had sold the paintings. If we continue here, what science showed, as they did, and this is what we'll be talking about very, very quickly, is that they were able to discover that there were a whole host of pigments that were used that could never have been used in the 1920s because they did not exist. And that is what we will talk about. And that goes back to this initial sentence of, within a painting, there is a record that an art historian cannot necessarily see. So, how does this work? Where does it come from? By the way, here you have an original me painting. If you ever see this in the Louvre or anywhere else, or in the Tate, it is a fake because it only exists here. But it's going to illustrate a little bit of what physics does. If you imagine this, you have a number of bells behind a curtain, and you're asked to give an idea of which bell is hanging where. Well, there's an easy trick. You take a hammer, and you hit through the curtain each of the bells and listen to the sound. And if you're slightly musically inclined, you should be able to identify which bell hangs where. What does physics do? Well, we do pretty well the same thing. We don't use a hammer, we use protons. Protons we accelerate, that's where the nuclear physics comes in, and we shoot them at a painting. If you remember that all paints, all pigments basically are formed by atoms, molecules, and as this proton shoots through here, the electrons are excited and then de-excite, we'll see that in a second, and emit not sound but X-rays. And if I can pick up those X-rays and compare them to tables, I can actually identify the elements that I find in these various pigments. Let me show you this in a little bit more detail. This is where the physics comes in, and I promise I won't be doing too much of it, but basically it follows the following way. If you're looking here at a hydrogen atom, the nucleus is in the center. Here you have, in this case, an X-ray that is absorbed. The electron moves by one orbit out, and then after a while will fall down and emit an X-ray. And ultimately, this X-ray corresponds to a very specific energy, and if we look at them, we recognize these series. We have basically catalogs of these, just as much as we have catalogs of sound, in a sense. And ultimately, that is what we can do. So what happens is that if we look here, one way of doing it is you have a sample, which in this case you can see is actually, could be a work of art, could be a painting, and you shoot actually general X-rays at it, and these X-rays excite the electrons. As they fall down, they basically emit very specific images. So this is what goes in, this is what comes out, and if I compare that to the catalog, I can say I have some copper, I have some zinc, I have some lead. And that is ultimately how it works. Where does nuclear physics come in? Well, you can do this with an X-ray tube, but you can actually, as I said, do it also with protons. The big advantage of this is that protons have a very specific energy and really hit at one very central spot. And that's what we see here. We basically use an accelerator. I won't bore you with the accelerator. It gives me my protons at a very high energy, so with a high velocity. The beauty of that is they'll hit a specific spot. If I want to go somewhere deeper, I just increase the energy. If I want to come out, I decrease the energy. That basically is what we do. So how does a lab look that has an accelerator? Well, this is our lab at the University of Notre Dame. A little known fact, so this is the nuclear science lab. The University of Notre Dame has the third oldest continuously in operation accelerator laboratory in the world. We're very proud of that. We have over 30 graduate students, 10 principal scientists, so about 60 people that work in this lab. It is fantastic. As I say, most of what we do is actually nuclear astrophysics, but we do work with a little bit with art. And so how does it work? We basically use this accelerator to produce our little hammers, our protons. And in this animation, let's hope that it works. It should. I tested it. It's actually made by one of my undergraduate students. I may have to. You will actually see how, in principle, this works. So we start out right at the beginning of the accelerator. We have several accelerators here, which is what complicates this picture. This is our largest accelerator. And so this is where we will zoom in. And this is what we call the ion source. That is basically where we start out with some material and extract protons and then very slowly accelerate them. And that is what you see here. You see this electron, you see it goes through a pipe that is actually evacuated. It continues here, for some reason it disappeared, and then is actually shot at a painting. No, we have never analyzed the Mona Lisa. I promise you, but my student thought it would be a good experiment. And so the idea is you shoot these protons and out come all these X-rays. You have a detector here, and this detects a number of these X-rays and allow us to identify the exact components that constitute the point that we're shooting at. So ultimately what we get is something like this. Again, if I were a musician, I'd hear a sound and I can identify it. As a physicist, I have a catalog. I know which of these energies the various elements correspond, and therefore I can find what the elements are. How is that important? How does art history come into this? Well, because art historians have done an enormous amount of work on this. They have analyzed paint pigments over the years. And here you have hundreds and hundreds. These are various white pigments, yellow pigments, red pigments, and so on and so on. The exact chemical composition of them. All of that exists in tables, and very carefully so. Many of them will have a lot of carbon, but most of these have at least one element that is very specifically a sort of characteristic to lead and yellow or cobalt violet or things like that. The other thing that they've done is they've established over the years all of these different paints when they were used. Some have been used for 1,000 years. Some have only become available very, very recently. And so you see these tables. So as you basically analyze a work of art, as you shoot it with protons and get out X-rays, I can figure out if there are elements in these pigments that should or should not have been present. Does that mean that a work of art is a fake necessarily? No. Why? It could have been restored. It could have been restored. That's where, again, the art historian comes in. The art historian say, no, we know that this work of art has been restored. Then we have to do an extra step. But if you start seeing elements that you shouldn't see, it should at least start to indicate something has happened with this painting between its conception and now. And so that's what we do here. If we look at various examples, here, Amedeo Modigliani. Now, it's pretty well known he has been copied, sadly, many times. That does not mean that if you have a Modigliani hanging at home, that it's a fake, but there are a lot of fakes, sadly. He was a sculptor, he was a painter, and sadly was copied a lot. And here's a typical example. This painting was actually submitted for an exhibition, retrospective of Modigliani. And the interesting thing is if paintings get submitted to major exhibits and end up in the catalog, that gives them already in the art world a provenance. It gives them a certain value. So it's kind of important to figure out if this is true or not. So what they did is they analyzed the blue that they find here. And what they found is a cerulean blue. Cerulean blue actually existed in Modigliani's time. However, it is known that he never used cerulean blue. Now, could he have made an exception? It's possible. Unlikely. Why? Because painters know how the paint that they use dries, how it ages, how it sees, how you can cover it. And it's very unlikely that a painter changes colors over time. They generally stick with the same because they know how they happen. And so ultimately, they did other tests and did find out that this was a forgery. This is important. Why is it important? Well, because sadly, more and more of these works of art really represent vast amounts of value. It's sad to know that nowadays many works of art are actually in boxes in two places. One is Zurich in a tax-free zone, and the other, I believe, that tax-free zone is in somewhere in Asia. I can't remember. And they basically have been there for years and years and years and get bought and sold. Their value has never been tested. They are just there and they're sold. But the reality is, as the value of these works of art increases, so do the forgers. The forgers are really good. And as you've noticed with Wolfgang Pultrachi, it didn't need much. Nowadays, we know that good forgers go and buy 8 old canvases, strip them, and use them. They become better and better. So as they become better, so science has got to become better. But again, science is only a part of a picture, but is important. Now, we've talked about fake or forgery. All of these techniques also really can help the art historian. Here is an example. This is the Brevarium van der Berg, which is a beautifully illustrated prayer book. And it is known, this is not a fake at all, but it was illustrated by 3 different painters around 1510, Simon Benning, Gérard Horenbout, and Jan Provost. They all illustrated it together. And now the art historians are trying to figure out who did what exactly, because it's interesting. Did they work together on the same paintings or stuff? And so what happens is the same type of analysis was done. Basically, these paintings were very carefully placed at the end of a proton line. I can guarantee you that when librarians come, they are very, very nervous very often about seeing their sort of works of art being put there. And we have to be very careful. You do not want to shoot a lot of protons at the same time, because you can burn a hole very, very, very quickly. So you have to be very careful. But this can be done. And so what happens is you get these types of analyses. You can look here. So we had, 2 paintings. One is the Virgin Birth here, and Saint Michael and a dragon. And so what they were looking at is, again, various pigments, the darker greens, the blues, the yellows. And again, you have to remember, each of these artists, yes, they mix their own paintings, but they tend to stick with exactly their own mixtures. And by actually analyzing each of these points and looking at the various contents, they could actually figure out which of these could be the birth of Christ, or the Virgin could be attributed to one or the other. And over time, recreate who did what. And that is a beautiful way of also, so this is far away from the fakes. This is really helping the art historian trying to identify by looking at things that are deep within that artifact, and it's something fun. This to the point where actually there is a museum, the Louvre. The Louvre has its own accelerator. It is actually called Aglaé, the Accélérateur Grand Louvre d'Analyse Élémentaire, that works 24 hours a day solely for the purpose of analysis of art. It is absolutely fascinating. You can see here, actually. So this is actually the type of setup. You have a statue here. I'll be talking about that in a few minutes. And various statues, and as they analyze point by point each of these points and look at the constituents, look at this X-ray characteristic signal to find out the constituents. This can be to try and understand the work of art, to understand how to restore it. Also, if you're going to restore something, you want to use the same type of pigments. So what are the original pigments? What are the new pigments? How can you change? All of those things can be done with this type of technique. If we look at here, this Parthian goddess of love, Ishtar, they originally actually thought that her eyes were glass, were colored glass. Actually, they found out that they were actually rubies. Well, that's very nice. But not only that, the beauty of that is that actually within rubies you have certain impurities, and particularly chromium and iron. Why are that important? Because those impurities come from, as the ruby is formed in the geological formation, it gets the imprint from that local geological formation. So if we look at rubies in general, and these are, you can look that there are 3 different types. What I'm looking here is actually simply the iron concentration versus the chromium concentration. And you're looking at rubies that come from various. These are the Burma rubies. These are more the Afghanistan and Sri Lankan rubies in Vietnam. And these are Thailand, Cambodia, and Kenya rubies. Their iron over chromium content is a sort of very clear signature. So what they did is they actually looked at the iron versus chromium content in this Ishtar goddess and actually found that, so the statue was found here, but the rubies came from probably a mine here. Why is that important? Because it tells the art historian so much about where this piece of art came from. How did it get from there to there? How did it get further? That is the type of information that can be found. That is an incredible source of information for art historians and to follow up this. So it's not only is it worth something, can I tell a story with this work of art? And you certainly can. Another example, which I won't spend much time on, is actually looking and analyzing inks. If you remember, people, monks and various writers would mix their own inks. By actually analyzing the inks, you can not only identify various writers, but you can also do some fun analysis. There was a whole analysis done by Italian scientists who looked at Galileo's writing over the years. And they could absolutely correlate when he had good years, good financial years, because he would use better inks rather than his poorer years. And it was absolutely correlate. And they were actually also able to reorganize some of his writings just by looking at the inks. It's absolutely fascinating. It's great fun. So let me say one thing. This is being done in various labs. You probably haven't heard much of what we've done. We tend, when I say we, it is the nuclear science lab at the University of Notre Dame, to stay away from authentication. We really do, what we mostly do is we teach the techniques and we support some of our local departments in some of their research. But we tend to stay absolutely away from any authentication because that brings with it an enormous amount of lawyers, and that's not what we want to do. So we stay well away from that. But let me give you some examples of some of the work that we have done, and actually looked at certain works of art that are in the various university collections, where university librarians were interested. Also, the interest of looking at the silver content of various Roman coins. And you can actually correlate that to the riches or the downfall of the Roman Empire. The inflation in the Roman Empire is actually shown in the coins themselves by, again, this non-destructive technique of simply shooting some protons at it and looking at the X-rays. It's absolutely fascinating. And here you can see that set up. Here again, this is a Mayan statue that we were analyzing. This is the end of the beamline. This is where the protons are coming from. This is the detector that detects the X-rays. And again, there's a very, very small, you have vacuum here, and this is in air. There's a very, very small window that the protons fly through, and then this is where you have the X-rays. What we also have here is actually a small laser light that points at the exact location that we're looking at, actually photographs it, because with each location you will get a spectrum. And then you can go back and see to which spectrum corresponds to which of the points that you were analyzing. This is actually a dinosaur tooth that we were analyzing. Again, when I say we, it's actually many students actually from anthropology that were doing this kind of work. It's a fun way actually of really introducing a lot of students who would have stayed a mile away from physics, and certainly then a nuclear lab, and that suddenly become totally enthralled in nuclear techniques because they see what it is teaching them, what the information that they can get out of it. And they get totally excited about it. It's great fun to see, and it's great fun to do, actually. We were actually able to even get Christ on the first page of Physics Today. I'll put that down as a feat of the University of Notre Dame. We were actually looking at this icon, and so you can actually see Physics Today. We managed, this is an article that a colleague of mine, Michael Wiesch, and myself wrote about this technique. We're actually shooting some protons onto the eye of Jesus, but we managed to get Jesus on Physics Today. We're quite proud of that one. So that's the sort of type of work we do once in a while. Some of the very interesting work that is being done by the anthropology department is actually looking at Mesa Verde black and white paints. A lot of work has been done on the potteries themselves, but not necessarily the paints. And what is interesting to know is that a lot of these Mesa Verde potteries and pieces of pottery that are painted in with this sort of black pigments that come from beeweed. And so what they did is actually analyze not only the content of these paints, but what they were specifically looking at, and we can see that on the next slide here, is that if you look at beeweed that come from various locations that are specifically identified for Native Americans that were living in that time, you can see that there is actually the sulfur versus chlorine content is very specific. So by looking actually at just these flakes of potteries and looking at the content of the sulfur versus chloride, they could actually identify which pottery came probably from which of these groups. It's absolutely fascinating what is really shows and gives you a dimension more to how these groups interacted, how they brought potteries with them, where they came from, and it's absolutely fantastic. Another type of advantage, this is also done by anthropology students at the University of Notre Dame. They're looking at silver versus lead and antimony versus lead in copper. Why is that interesting? Because if you're looking at native sources of copper, they tend to have silver to lead contents that sort of are in these sort of concentrations, whereas European tend to be up here. Same with the antimony over lead. So what did they do? They looked at various various copper fragments and did an analysis of them. And what were they able to learn is actually, were these various groups already at some point in contact with Europeans or not? Did they have trade with Europeans? Yes or no? That is an enormous dimension that would not have been available to anybody by simply looking at the copper itself. And here you can totally non-destructively, very, very quickly, within a few minutes, find out exactly what that sort of information. And that's fascinating. It brings a sort of piece of the puzzle. So this is where I'll stop talking about PIXI, but I hope I've been able to give you a little bit of a flair of what we can do with PIXI, this sort of identification of the origin or the content. Yes, we can do a little bit of dating, but I haven't talked at all about one of the other big techniques, and that I'll bring up very quickly here, which is radioactive dating, which is another big technique from nuclear physics, and that is oh so important. And let me bring up Rasmus Nierup. He was actually the author of the big classification of the Iron Age versus the Bronze Age. And you can recognize he was actually charged with classifying the royal collections. And you can sort of see already here a certain frustration when he wrote, everything which has come down to us from heathendom is wrapped in thick fog. It belongs to a space of time we cannot measure. We know that it is older than Christendom, but whether by a couple of years or a couple of centuries or even by more than a millennium, we can do no more than guess. Well, truth is, we can now with nuclear techniques do a lot more than guessing. So how does that work? I will not bore you again with radioactive decay, but just basically bring up the following. If we are looking at radioactive decay, you're looking at a parent nucleus that is called unstable, that as it decays, emits a certain amount of radiation and ends up as a daughter product. What does that mean if I look very specifically here? Let me give you an example. So if we have potassium-40, it decays to argon-40. The way that this happens is according to the law of radioactive decay, which is a purely statistical law. It follows this absolute precise. Don't worry about the math too much, but basically it is absolutely statistical. What it says is every specific element has, or isotope has, a half-life. If it has a half-life of 30 years, what does that mean? That means that if I have 1,000 atoms of a specific type, after 30 years, I will have 500. After 30 years, I have 250. After 30 years, you get the idea. And so this is a very nice clock. So what we can do, and what this basically equation tells us, is that there is a time, there is this information that nuclear physics brings us, which is this half-life. If I know how many atoms are now in a specific sample, and if I know how many should have been, I can extract the time. And so I can see this. This is carbon-14. This is this very well-known carbon-14 method, where the half-life is 5,730 years. That means after 5,730 years, I have exactly half the initial amount, and so on down. And so we have all these isotopes that are, some have very, very long half-lives, some shorter, and they allow us to basically, if we're looking at carbon-14, as I look at the years that pass, I go basically from 5,000 to about 35,000. That's history and archaeology. If I'm looking here at uranium-235, which has a much longer half-life, I can go from about 1,000 years, to 1,000 million years to 7,000 million years. So that's definitely archaeology and anthropology. And if I look at the deep evolution and geology, if I'm looking here at rubidium, that times is in billions of years. So that is extremely important. So ultimately, what am I looking at? If I'm looking at, and that's one technique that I'll talk about very quickly now, is carbon-14. Carbon-14 is produced naturally in the atmosphere. It basically, cosmic radiation interacts with nitrogen in the atmosphere and produces carbon-14 that has this long half-life. This basically follows the same standard carbon cycle than everything else, and basically enters trees, soil, gets eaten, etc. As long as something is alive, it is basically exchanging with the atmosphere, and therefore any carbon-14 that has disappeared or decayed gets replaced by new. And you have a sort of a stable concentration of this carbon-14 that is in your body. As a plant dies or a person dies, they do not have that renewal. So therefore, we can basically, that carbon-14 will start decaying. If I know how much something, let's say a bone, should have had as it was alive, and that basically is relatively easy to discover, and I have a specific sample, if I can find out exactly how many carbon-14s I have left, then ultimately I can tell the exact amount of time that this bone has resided somewhere. It's an incredible, powerful tool. The question is how do I measure what is left? And so ultimately, don't worry about the formulas, but ultimately what I'm really interested in here is this time. And what this whole formula tells me is that I simply need one ratio, the ratio of the carbon-14 to modern that is there now. Once I have that information, once I can measure that, I'm done. So one easy way of doing it is simply waiting for the decay. Wait for the radiation of the decay, and that'll tell you how much you are. So if I look at 1 milligram of carbon, modern carbon, that has about 6 times 10 to the 7 carbon-14 atoms. That corresponds to 1 decay per hour. Well, if you have more sample, this will increase, so that'll decrease your counting time. If you have time, you can simply count enough, but you need at least 10,000 counts to have good statistics. It means you have to wait. Now, the problem is, many archaeologists will not be too happy if after having spent a lifetime digging something up, you say, well, I need about 1 kilogram of that bone, please. I'll burn it, and then I'll measure the carbon-14. They'll say, no, thank you very much. So rather than wait for the decay itself, why not take a very, very small sample? And I will spare you the details of the exact technique, but ultimately what nuclear physics does, and that same accelerator that gives us the protons, also actually allows us to put some material in what is called the ion source, that's the beginning, and we can tune this whole accelerator to a specific mass. So if I'm looking at carbon-14, I will tune this to mass 14. I'll need the rest of the accelerator to get rid of everything else that has also or near enough mass 14s, but ultimately you'll have to trust me on this if you don't want me to bore you for a 3-hour lecture on accelerators, and I promise you I won't do that. But the idea is that we can actually extract that information. It really is, we can use the accelerator as a needle in the haystack tracing tool. Let me give you an idea of when I'm talking about what's the size of the haystack and what is the size of the needle. This is Lake Michigan. It's kind of big. It contains, the current volume is more or less 5 times 10 to the 15, although this is the number from last year. We've had so much rain that it probably has increased quite a bit. But that gives you an idea. That's the current volume of Lake Michigan. This is the volume of an Olympic pool. If I pour the Olympic pool into Lake Michigan, that basically ratio of the Olympic pool to Lake Michigan is about 10 to minus 13. That is the ratio of carbon-14 that I'm looking at in samples. That's a very big pool, but it is nothing compared to Lake Michigan. Now that is in that range of 10 to minus 12, 10 to minus 13. Take the bottle of vodka here. I know this is heresy, but trust me. Pour it into Lake Michigan, that is 10 to minus 16. We can still measure that. Actually, the lowest concentrations that we can measure are 4.2 10 to minus 17. That's about the minis that you used to get on planes before they stopped serving drinks. That's the power of this technique. So ultimately, it is we really can look at enormous haystacks and very small needles and extract that information. So if I'm now given a sample and asked how much is left of a specific radioisotope, I can actually measure that. And from there, we can extract a time. That is the important thing. Here is actually a group of my students. Again, we don't do this in works of art, but the technique is the same. We use this mostly for nuclear astrophysics, but the technique is the same, and I'll illustrate it in a second, very shortly. But the idea is very simple. You get your sample, you basically burn, but you only need a few milligrams. So the archaeologists generally don't mind if they give a few milligrams, a little bit of a bone or whatever. You basically pass it through the accelerator, using the accelerator to, yes, accelerate, but also as a sort of mass separator. And ultimately, you will get a concentration at the end. And if you compare that concentration with what you would expect, you can extract a time. Let me give you a very quick example that you may be familiar with. a frozen ice mummy. And this one particularly is a body found in the Tyrolean Alps. This was actually in the 80s. It was Ötzi, as he is now very charmingly called. So this is the Utstala Alpe in Austria. He was actually found, this was absolutely unsure at the time if Ötzi was not actually a skier from a few years ago that had simply reappeared. So for the first 24 to 48 hours, it wasn't really treated as an archaeological site, but very quickly they identified that, no, this was way more than that. This was actually a mummy that had appeared, and so started to do a lot of work. And obviously it was of great interest to know, where did this person come from? How long had that person been there? And so an enormous amount of work had been done. By the way, if anybody, once all of COVID is by and goes to northern Italy, Alto Adige, there is in Bolzano a beautiful museum where he is preserved. And I strongly recommend it. Plus Alto Adige is absolutely wonderful place in the world. So well worth a trip. But so one of the things that they were looking at is the age. And so samples were given to a whole bunch of universities, the ETH Zurich, University of Oxford, University of Uppsala, and the University of Vienna, Vera. That was at the time when I was a PhD student. God, that's a long time ago. And ultimately what happened is they ultimately found the age. And I will actually show you this very quickly here. So not only did they get samples from the body itself, but from a lot of equipment that was identified as belonging to the Iceman. And each of these was analyzed separately. Most of the labs got various samples, didn't know what they were getting. And if you actually look, the correlation is absolutely superb between the Iceman's body, the equipment. You can see the bow, the quiver, all of these, and they beautifully align. Now, obviously, a lot of people say, well, yes, and had you taken anything else, would you have seen some different results? Well, they thought of that at the time too. And ultimately, you can see actually here, when they took a lot of various altitudes and mosses that were very clear that did not necessarily belong to the Iceman, you can see that data is all over the place. Obviously, you'll find some that will correlate, but this is totally... and so this is a fantastic technique. But if you're looking at Ötzi, and for those of you that have perhaps followed that story, chemical analysis of his stomach have managed to not only identify where he came from, but where he grew. Analysis, scientific analysis of his teeth and his enamel, of exactly where he was born. They literally could retrace pretty well everything in the life of Ötzi, although they did miss the arrow that was stuck in him. They only found that a few years ago. But it is absolutely fascinating what was able to be found. And that is what some of the nuclear techniques can find. There are many more nuclear techniques. I'm not going to bore you. I've bored you enough as is. But what I want to leave you with is that if you're looking at authentication, either to find out its value or its intrinsic value, it's not only the science. You need science that will give you need the art historian, you need the historical background, you need the provenance. You need all of those things to come together, and each is a piece of a puzzle. And when you put that together, you have a pretty good idea of what you're looking at. And that's great. And for us, it's very exciting because it allows us to sell nuclear physics as something exciting to people who would never touch it with a broomstick, and who are really excited about this. And it allows us to do something else and something that is fun, and people can relate to that. So with that, I will stop here. As I said, these are just but two in a whole array of techniques. Thank you very much. I hope I didn't bore you too much, and if there are questions, I'm more than happy to try and answer them.
Well, Philip, this is Martha off camera, so the voice in the sky. First, I just want to say, as someone who studied art history, I really appreciate you giving me permission to not fully understand everything. But I also really, I think this is such an interesting example of the hard sciences and the social sciences working together. And that seems to be something you kind of enjoy about this application.
Oh yes, this is definitely it. It is this working together, and it really is when you show these techniques and talk to an anthropology student who would never look at physics in anything else than absolute horror. They suddenly go, "We can do that," and then when we show them how to use it, they become totally excited, and it's great fun. And it also shows and brings physics and nuclear physics nearer as being one of the societal tools that we have at our disposal.
And so you mentioned that at Notre Dame, you're mainly teaching this. Notre Dame, you're not doing this work specifically. Have some of your students gone on to focus on art forgeries at all?
So I don't know if necessarily art forgeries, but a lot of the anthropology students have gone on to analysis of art. Some of the students have gone on to areas that are very near to that. So absolutely, yes. And what it shows is that you really have to learn these techniques, because what happens, especially when you're doing art authentication, is, and you end up in a court of law, and you go over these whole discussions of, well, these are measurements with an error bar and things like that. Ultimately, the art historian or the anthropologist or the has to understand the physics behind it in order to understand what are the limitations of the technique, but what are the riches of the technique.
Yeah, I was intrigued too by the idea that you could damage a piece of art or a sculpture or anything.
Oh, very easily, actually. When in Vienna, where they did some of this work on Ötzi, about 10 years ago, they were doing some analysis of some Dürer work, his first, and so we're using that. And obviously, there was a lot of work that was first done on how much of a proton intensity can you actually shoot on a page without burning through it. But then not only that, if you do warm it up even slightly, does it damage, does it leave any marks? And so a lot of work was that. And even after all of that had been done, when they took the original Dürers and put them there was a great deal of nervousness on both sides, both scientists and everything. But yes, you have to be very careful. But ultimately, you can dial down the intensity and simply increase the time a little bit. But the reality is an analysis like this can be done in 10 minutes rather than hours and hours, and is totally non-destructive. And that's the strength of it.
Yeah, well, we were wondering if people needed to sign waivers, collectors or museums, if there was...
So that again is why we stay out of that. We really do mostly as a teaching tool for our students. We serve the Notre Dame community in general, but we tend to stay away from, and we quite often, especially after talks like these, then get requests, so can we send you these works of art? We try to stay away from this, because with it brings a whole frame load of questions, of legal questions, of all of that. And that's, we really are a teaching institution. For us, it's the fun of it. And we leave it to the specialists. But what is really growing, and you can notice them around some of the big cities, there are more and more companies that really are dedicated to this. They have a whole slew of different people that work in different fields, and they all work together. And they have accelerators and things like that allow them to do this type of work.
And was it the Louvre that you mentioned has their own? Are there other museums that have their own too?
No, actually the Louvre is the only one that has one. The others tend to either farm out to the Louvre then, or to other labs. Some nuclear labs have dialed down much of their, would I say, nuclear physics research, and have really dedicated themselves to actually work. And if you look there is an AMS lab at Oxford that practically exclusively works in archaeometry. So in that case, it's other universities that have transformed some of their nuclear physics work rather more in the analysis work. And so that's the trade-off that they've done there. Running a big accelerator at the Louvre like Aglaé is not easy, because obviously it's very difficult, and it needs a lot of people.
So this is kind of more about you and your personal interest. It was wonderful to listen to you, because it seems like you really love this application. And what is it that you primarily focus on?
So the primary work of my graduate students is actually looking at the interior of stars with accelerators, which is a totally different topic. I'm happy to talk about it one day. That's most of what we do, but it's very abstract. And it's very often very difficult to get people, except that are absolutely fascinated by astronomy or deep stars, interested in this. This is, first of all, something that gets us out of the lab. I actually started this by using AMS to do some dating of groundwater using Krypton 81. And I was able, as a graduate student, to go to Australia to get some groundwater. I was able to go to Antarctica. So it got me out of the lab, and that's great fun. But what it really is it's first of all fun because it allows you to discover different worlds, different applications, and that's always, I think, fun. But it is a great way of selling physics and of showing the strength of it, because very often you get this sort of question of what is physics? Why do we care about the formation of the universe? Well, it is exactly those techniques that we were able to use and apply here. And that's the important thing. And we can get really people fired up that would have never thought of physics and think, oh, this is cool, this is really exciting. And that's a great way, and it's a great way of getting students excited. Michael Visha, myself and a few others have developed a whole series of lectures at Notre Dame on the physics of archaeology using nuclear techniques. And so that's our way of selling nuclear physics to a lot of arts and letters students by each time taking a specific example and explaining radioactive decay and how you use it, neutron activation, all of those things through art, and that's great fun.
We've got, I think, just one last question before we close. Do you see any future applications? I mean, either related to studying art and archaeology, or other applications people would be interested in knowing are out there or could be possible? So
obviously there are many different applications of nuclear techniques. Now, are there going to be more and more use of nuclear techniques? And the answer there is yes, and it has to. Why? Because of these vast values. So next time somebody is going to buy a multi-million Picasso, they will not only nowadays rely anymore just on the provenance and the identification. They will want that analysis done. So what we're noticing is that more and more auction houses, they were burned several times. Forgers are getting better and better. As the forgers get better, so do the techniques. So we have to evolve, and so there is a lot of development there. And how can we refine this? How can we ever increase our sensitivities? So there's a lot of work there. But if you're looking at general applications of nuclear physics, I mean, just if you're looking at the medical world, if you're looking at the analysis of materials, there's a lot of work that is at Notre Dame that is being done to analyze actually lead in paint. That is so important, lead in water. We have vast programs. We have actually a whole accelerator that is dedicated to analyzing various fluorinated products in food wrappers, because those are so bad, looking at lead. And the beauty of these sort of nuclear techniques is that you can do hundreds and hundreds of samples in a day very quickly, rather than to have to wait. And so there are a lot of the applications, and it's really important to see that nuclear physics is a societal tool that brings a lot. So yes, I see a lot of future in this, and I see actually more and more students that come and that are really interested in the applied side of nuclear physics, what we can do, and that's nuclear forensics, and it's so many different things. So there are some great things coming along, and I'm very excited about that. But I think I've bored people enough, and so I will stop here. But I'll first of all thank the library for this wonderful opportunity to present some of the work that we do. So thank you for having me. And I really enjoyed it. And thank you, Sun Valley, for giving me the respite after a year of isolation in Chicago. And for any of you that I have bored too much, please don't run me over on the slopes tomorrow. Thank you very much. And I really enjoyed this evening, and I hope I was able to show you some of our techniques. On this note, I shall mask up and wish you all a happy good evening.